This is the pre-recorded lecture for Friday, March 7th. Just so you guys have it, I'm doing this from home. So if this is a little bit of a different setup, that's the only reason why. We've just spent an entire chapter, several weeks on derivatives. Let's go the other way. Let's do double integrals. All right, wait a minute. If I'm going to do a double integral, I'm going to start with the idea of a definite integral. And let's start with the Calc 1 definite integral, the integral from a to b of f of x dx. We had our graph of f of x, we had our point A and our point B, and we got an area. But we got that area by cutting this into a bunch of little strips and taking a point from each one, and then letting the number of strips get bigger and bigger and finding the area of all of those rectangles. So it was the limit as n went to infinity of the Riemann sum, I goes from 1 to n, f of xi star delta x, where xi star was some point in the ith subinterval. F of xi star, thus the height, gave us a rectangle. We added up the area of all of these rectangles. But now I want to think of how to do the same idea with a surface. So I've got some surface S in 3D living above the XY plane. What I want to do is take an area in the XY plane. Let's call this R. You'll notice I've drawn that R sideways because if I go over here and just look at the XY plane, then the R will be oriented correctly. Its bottom faces the x-axis. And we're going to say that this goes from A to B in X and from C to D in Y. So this is the rectangle made up of the interval AB times the interval CD. How do we divide up this rectangle? Well, we're going to do this rectangle by partitioning it in both X and Y. So we get a little grid. And in each grid, we're going to take a point. That point will be xi star, yi star. And now you'll notice in this case, I have 5 across the x and 4 across the y. But if I say that we're going to do n parts here and m parts this way, well, then I would have a sum, but it would be a double sum. We did this in chapter 2 back in discrete. So I'm going to think of adding up the area. Well, not the area this time. I'm going to think of taking each of these and making a little tower. So I will have a z value, f of xi star, yi star, times the little area, delta A, where delta A is the area of one of those blocks. And this will sum, well, let me change this. Instead of I in both of them, we'll call it I and j. That way the row and the column can be counted independently. We'll go I from 1 to n, and we'll go j from 1 to m to get all the parts in j, to get all the parts in I. And this is going to be our volume. Now, it's kind of hard to picture this. Page 989 has a picture in the textbook, but I thought I'd bring you a surface. So here is one of our 3D surfaces. I printed this. This is our cubic surface that we talked about Monday, Tuesday, this is our monkey saddle surface. And I'm going to think about a grid underneath this surface. Now, in my case, I'm going to make a grid that's 6 by 6. There's my grid. But notice each of those grids, I pick a point and I get a tower. And I think of this sum as the total volume of all of these towers. So like we did area under a curve, we're going to do the volume under our surface. Now, again, I have this one. The textbook, page 989, shows our grid in X and Y. And then we take this little rectangle down here in the XY plane and we make a bunch of towers. We add up the volumes of these towers. And here's our volume using this double sum. So my goal is to try and turn what is, I hope pretty clearly, a new kind of Riemann sum into an actual integral. Now, just like in Calc 1, sometimes we didn't need any calculus to do this. We were able to do this just by doing geometry. So here, let's consider the surface formed by z equals the square root of 1 minus x squared. And we're going to go from -1 to 1 in x and -2 to 2 in y. Now, if I'm doing this particular behavior, wait a minute, this function has no y's in it. That makes this a cylinder. And not only that, the curve z equals 1 minus x squared is the same as z squared equals 1 minus x squared, or x squared plus z squared equals 1. That's part of a circle. That's a semicircle. And in the y direction, it goes from -2 to 2. So this is a cylinder made up of a semicircular arch going along the y-axis. Oh, wait a minute. The area of a cylinder is base area times height. The base area is half the circle of radius 1. Well, that's just pi over 2. The height of our cylinder is 4, so the volume is pi over 2 times 4, or 2 pi. As an integral, notice I called this a rectangle R, I would write this as the double integral over the rectangle of our curve f of xy dA. Gee, that looks familiar. Notice instead of doing the from A to B, I just said over R because the whole bottom, the base of this, isn't just the interval from A to B, it's a rectangle. So instead of saying I went from A to B, I'll say I went over this entire rectangle R. By the way, that means that when we did it in Calc 1, technically, I could have written them as over the integral there to, sorry, over the interval there to. It just didn't seem as appropriate to write the integral over AB. But that really means the same thing as the integral from A to B. So here, I'm doing my integral over R. Now, this problem got done without any calculus. But I defined my volume using this sum, so I'm going to think of my integral f of xy over the rectangle R as the limit as n goes to infinity and as m goes to infinity. So that's the same definition we had for a double integral in for an integral in one variable, now done in two variables. Which means if I want, I can do more rectangles to get better sums. Again, I could approximate these by, finding actual points. Like this problem we just did, I could say, well, instead of going from geometry, let's actually do calculus, and I'll compute the actual sum, the double integral over the rectangle, square root 1 minus x squared dA, where the rectangle goes from -1 to 1 and -2 to 2, x and y respectively. Oh, -1 to 1, -2 to 2. Here's my rectangle R. I could break this into, say, 8 pieces. And I could take the midpoint of each one. Okay, wait a minute. I know these coordinates. Here, x is a half. Y is 1.5. Here, x is a half, y is a half. Here, x is a half, y is negative a half. Here, x is a half, y is negative 3/2. Over on this side, all the y values stay the same. It's just the x's become negative. And the area of one of these squares would be 1 unit wide by 1 unit tall. So my area is 1. Now I just need the z values for all of these points. Well, then I take these numbers and plug them in. 1/2 squared is 1/4. So square root of 1 minus 1/4, that's square root of 3 over square root of 4, square root of 3 over 2. But that's going to be the same for all of these x values because they're all 1/2. And over here, the x values are all negative 1/2. So I can approximate my volume by doing the midpoint sum. Now, I goes from left to right, 2 left to right, j goes top to bottom, 1 to 4, f of xi star yi star delta a, in this case, that's the double sum of root 3 over 2 times 1. But that's a constant. So I just added up 8 times, and I get 4 square root 3. By the way, that's roughly 6.93. What was our actual area? Oh, right. 2 pi, which is 6.28. Not that far off. Instead of getting the integral, I got the approximation. And this seems to be an overestimate rather than an underestimate. I think we'll have to figure out why later. Normally at this point, I would ask if there were any questions. You're not here. You can't ask me questions. But I would point out to you that if you do more rectangles, you'll get a closer estimate. If you do even more rectangles or even more rectangles, so this is 16 rectangles, this is 64, this is 256, this is 4. This is on page 991. And here's their midpoint approximation using 4 rectangles. If I didn't actually have a formula, I could use a contour map to approximate my values, like here. Here's a map of the state of Colorado. Best part, Colorado is a rectangle. Colorado's, well, almost. It's close enough to a rectangle. 388 miles across, 276 miles at the top. So I could make, say, 4 divisions by 4 divisions, get 16 rectangles, and I could use these contours to determine the z-value in the middle of each rectangle. Now they've actually done that picture here in the next page, and you can see they put a dot in the middle of each one. So it makes perfect sense for me here to say in this upper rectangle, that's this contour, and if I follow that contour around, I see the value on it is 12. So this midpoint height is 12. This midpoint height is 16. This one, well, probably 18 would be my guess. It's not quite 20 and it's not quite 16, so. And we can approximate all of these. The size of one rectangle is 276 divided by 4 times 388 divided by 4, which is 1/16 of those numbers, 6693. Add them all up, and you get the total snowfall in cubic inches. Oh, no, sorry, inches times square miles. We'd have to do some unit conversion to get this to be a consistent unit to give me the amount of snow that fell in Colorado in the month of December, December of 2006. Hmm. Now, my problem is that I don't like doing Riemann sums. I hate Riemann sums. It's one of the things I like most about calculus is that I can do calculus instead of just mindlessly adding numbers. So I'd like to actually do this with some calculus. But before I do that, there are a couple of properties I need to mention. Since these are integrals, it's true that the integral properties I have carry over. In order to do the integral of a sum, you do the integral of the first thing, add the integral of the second thing. If you have a constant, you can take that constant out front. And if you know that f of x is bigger than or equal to g of x is bigger than or equal to 0 on the entire rectangle, then the double integral of f over that rectangle will be bigger than or equal to the double integral of g over that same rectangle. These are the same properties we had in Calc 1 for the definite integral, which we did back in Chapter 5. Hmm. Okay, I get it. I don't particularly like it because it doesn't look like I'm doing anything that's actually calculus yet. So let me ask what I hope is a reasonable question. Let's do the double integral on the rectangle R of x squared plus y squared dA, where the rectangle R is 0 to 2 in the x by 1 to 3 in the y. Now, before I actually do this problem, let me think about this expression here, this double integral, measures the volume under the shape z equals x squared plus y squared. What's that shape? Well, I'm going to go ahead and physically graph this in my grapher on the MacBook, but because I'm here at home, I think it'll be easier if I do this on my iPad, but we can do the same thing on the MacBook grapher. So I'm going to go to the quick graph program that we were using the other day, and I'm going to get rid of this equation, and I'm going to put in z equals x squared plus y squared. This is a paraboloid. It's a paraboloid oriented upward, and I'm graphing in the rectangle that goes from 0 to 2 in x and from 1 to 3 in y. So I want the column whose lid is this upward curving paraboloid. I want the area under the paraboloid. Okay. Okay, now I know what I'm actually looking at. Volume under the paraboloid, z equals x squared plus y squared, over the rectangle R. I absolutely do not want to do a Riemann sum here. Doing this Riemann sum would just be unpleasant. So I say to myself, I know how to integrate. But the problem is that I don't know how to integrate two different variables. So what if instead of integrating two different variables, I did what I was trying to do with derivatives, and I did a partial integral, like a partial derivative. We're going to call these iterated integrals, because I'm going to have to do more than one of them to finish this problem. Let me just think about the x part of this problem. In x, we're going from 0 to 2. Well, let's do this integral. What? Hang on a second. When I did partial derivatives, what did I do with the other variable? Oh, right. The other variable was a constant. So we're going to treat y here like it's a number. And we're taking the integral. I'm taking the integral in x. Well, the integral of x squared is 1/3 x cubed. And the integral of y squared, well, y squared is a number. The integral of 3 is 3x. The integral of 7 is 7x. The integral of y squared is y squared x. But there are numbers here. So I need to remember that I am evaluating this integral from 0 to 2. And those are x values. So I even wrote the little x right there to remind me these are x values. So plug in those numbers. If I plug in 2, I get 1/3 8 plus y squared times 2. If I plug in 0, I get 1/3 0 plus y squared times 0. As a matter of fact, this whole term is 0. So I get 8/3 plus 2y squared. A function in only y. Hey, wait a second. I did an integral with respect to x, and what was left behind had no more x's in it. But up here, this problem is a double integral, which means I should really do my integral in x and in y. So let's take this result that comes out, and let's do the integral here in y. The integral from 1 to 3, 8 thirds plus 2y squared dy. Now that's a Calc 1 integral. As a matter of fact, it's not even a difficult Calc 1 integral. It's polynomial. The integral of 8 thirds is 8 thirds y. The integral of 2y squared is 2 thirds y cubed. Plug in 1, plug in 3. There's only one variable, so I don't have to indicate which variable I have. So when I plug in 3 and 1, I get 8 thirds, 3 minus 1, plus 2 thirds. 3 cubed is 27, minus 1 cubed is 1. So that's 16 over 3 plus 26 times 2. 26 times 2 is 52 over 3. That's 68 over 3. I claim that's the right answer. That's the volume under the paraboloid. This is an iterated process. I had to do two integrals to get one answer. And it was really one integral inside the other. If I think about the way I set the problem up, this rectangle, remember, went from 0 to 2 in x and 1 to 3 in y. What I really did was I said, oh, I'm going to do the integral in x first. 0 to 2 dx. I did that part. And then I did whatever the result of this was. I did that integral dy. Hey, one integral inside the other. I'm actually going to get rid of that extra set of parentheses. I don't think it's necessary. Instead of doing a double integral dA, I did this iterated integral. Two integrals, one inside the other. And that, oh, wait a minute, copied it down wrong. That's a y on the end. Be careful. You have to have both the variables. That is an iterated double integral over a rectangle. I like that. But wait, there's more, right? Hang on a second. I did this integral in x first. What if I do it the other way? Let's try this same problem, but reverse the order of integration. So first, I'm going to do the integral in y. And then I'm going to do the integral in x. Now, if this is done correctly, I should get the same answer if I did it right. So let's cross our fingers and hope. Let's see. If I integrate with respect to y the first time, then x squared is a constant. So I get x squared y. The integral of y squared is 1/3 y cubed. That is evaluated from 1 to 3. I haven't finished the integral dx, so the integral dx is still there. I work out this number. Well, this won't really be a number. It'll be an expression in x. X squared times 3 minus 1 is 2x squared. 1/3 times 27 minus 1. That's 26 thirds. Wait a minute, that's a number. That's fine. So I get 2x squared plus 26 over 3, and I'm integrating that dx. Oh, I know how to integrate dx. I'll get 2/3 x cubed plus 26 over 3x. Plug in 2, plug in 0, and subtract. That's 2/3 times 8 plus 26 over 3 times 2 minus 0 plus 0. Notice that's 16 over 3 plus 52 over 3. That is exactly 68 over 3, the same thing we got before. Hot damn, we did it. Now, at the moment, in the back of my head, I hear you mixed the order X and Y. And I go back to last week and I say to myself, I mixed the results, I mixed the order, and I got the same thing. That was Clairaut's theorem with the derivatives. So just like Clairaut's theorem, it turns out that when I deal with a continuous function, the order doesn't matter. This result is called Fubini's theorem. I'm going to use this name a lot moving forward. Fubini did a lot of work here. If f is continuous on the rectangle R, which goes from A to B in X and C to D in Y, then the double integral over R, f of xy dA, is equal to the integral from A to B, the integral from C to D, f of xy dy dx, and is integral from, equal to the integral from C to D, integral from A to B, f of xy dx dy. Now, being continuous over the whole rectangle is a strong condition. So we can actually weaken this a little, and in some cases have it be like piecewise continuous, as long as it's only discontinuous on a finite number of nice boundaries, just like we were able to break up, go from A to C and C to B. I can go from A to B1 and then B1 to B2 and break up the X in one direction. Or maybe I need to break up the Y. We'll figure out how to deal with other boundaries later. But as long as I have nice boundaries, Fubini's theorem actually does an amazing job here. Proving this is a pain in the ass. I'm not going to. This is usually proved in a graduate course in calculus. Books like Royden's Real Analysis or Torchinsky's Real Analysis will give you a proof if you really want one. I don't think any of you do. Again, normally I would ask, got any questions? You're not here to ask questions. But if I think about this, the partial integral has a nice visual. When I did the inside integral dy, my result was something that was only in x. When I did my inner integral dx, my result was something that was only in y. So I can think about what we've done as saying, I'm going to take my function of two variables and do one direction's integral, whether it's the x direction or the y direction, and then I'm going to move that the other way. Let me go back and draw that rectangle again. Remember, our rectangle R goes from A to B in X and from C to D in Y. I can think of if I do the Y integral first, I've gone this way. And I get rid of the Y's, and then I move that from left to right in X. Or I can say, oh, what I really want to do is go from A to B in terms of X first, and then go from C to D. So this one was dy first, then dx. This one is dx first, then dy. Oops, can't see the bottom. There. At the bottom of page 994, we actually see a visual that I think is amazingly powerful. Figure 11 and 12 here. When I do this integral, I'm going dy first, and I build the result that's a function of x, and that's an area. It's the area under the curve from C to D. And then I move that back and forth in x, and it changes shape. So I'm actually measuring how this area. Wait a minute, when we did volumes, we sliced up the loaf of bread back in chapter 6. This is that same slice, only this time we went y first, then x. Down here we go x first, and then we move it in the y direction. So we're slicing these up. By the way, there is an animation of this available at the textbook website. If you search for um, Stewart's calculus, you'll be able to find all of these TEC visuals. There's a lovely little movable back and forth here. By the way, here's a short bio of Fubini. So let's actually do a problem using Fubini's theorem from start to finish. I'm going to do the integral from 0 to 2, integral from 0 to pi over 2, x sine y dy dx. Now this means to start with, I am treating y as my variable, so x is a constant. Okay, so I'm going to do the integral sine of y. The integral sine of y is minus cosine y. But don't forget the x. The x is a number. The x stays there. Now I did the integral in y. Notice that these two are on the inside, so these are the numbers that go with y. Y equals 0 to pi over 2. But that also means my dx and the integral symbol in x are still there, right? Okay, cosine of pi over 2. Cosine of pi over 2 is 0. Minus x times cosine of 0. Cosine of 0 is 1. Wait a minute, that's just 0. That's plus. So I get the integral from 0 to 2 of x dx. That was nice and easy. 1 half x squared, evaluated from 0 to 2. Half of 4 minus 0 is 2. Yay! Notice I can do it in the other order. Same integral. I've reversed the order of integration. Instead of going dx, dy dx, I'm now going dx dy. That means I have to reverse the numbers so that the inside numbers go with the correct differential. Integral of x is x squared over 2. The sine y is a constant, so it stays there. I haven't done the y part, so the y integral and the dy are still here. This gets evaluated from x equals 0 to x equals 2. I've only done the integral part in x. If you really wanted to, you could put this bar here and just treat the sine y like it's a number just sitting there waiting to do nothing. 2 squared over 2 is 4 over 2. That's 2 sine y minus 0 sine y. Two is a number, it stays there. The integral of sine is minus cosine. Cosine of pi over 2 is 0. Cosine of 0 is 1. And I get the same result. It worked. It worked. Now, I wrote these out as iterated integrals when I first wrote them down. Sometimes we write down the integral as an integral over a rectangle, and then you have to figure out which way you want to write it. Double integral over the rectangle R of y sine xy dA, where R is the rectangle, 1 to 2 in x, 0 to pi in y. Now, I would recommend that you pause the video here for a second and think about which way you want to do this and try it. One of these ways is going to be easier than the other. Why would that be? So give yourself a minute and then we'll come back. So I'm trusting that you've taken a minute. We're back. If I try and do this integral with respect to x first and then y, wait a minute. If I've written a dx dy, then on the inside integral go the numbers 1 and 2, and on the outside integral go the 0 and the pi. Why is this a benefit to me? Because here I have sign of ugly stuff. I should do a u substitution. If I let u equal xy, but I'm thinking about x as the variable, then I really think of the derivative du dx. That's really a partial. That's a partial derivative. But the derivative of x is 1. So y is a number, and really that means that du is y dx. I have a y to go with my dx. I can do a u substitution here, and it'll work. If I do this, I get integral sine of u du. There's still a dy out here. 0 to pi dy. Now I have to ask you the question, what are my limits here? Two choices. I can do this in x and y, or I can push I can do this in x, right? X equals 1 and x equals 2, or I can push the limits through the substitution, which gives me limits that look like functions of y. I don't think I want to do that right now. So I'm going to write x equals 1, x equals 2. We already did the antiderivative sign up there. It's minus cosine. So I get 0 to pi minus cosine of u, x equals 1, x equals 2, dy. But u is xy, so that's minus cosine xy, 0 to pi. Well, now wait, these are x's. So put those in for x. I get minus cosine y minus negative cosine 2y. I know how to do that. This one's the easy one. This one is a u sub. U equals 2y. The antiderivative of cosine is sine, so this is minus sine of y. The antiderivative of cosine is sine plus sine of 2y. Evaluated from, oh, wait a minute, there's a 1/2 there because of the u substitution from 0 to pi. An amusing thing happens here. If I actually work this integral out, sine of pi is 0, sine of 0 is 0, sine of 2 pi is 0, sine of 0 is 0. This integral is 0. I did an awful lot of work to get a zero. What does it mean that this integral is zero? It means that my total volume is zero, but some of that volume will be above the xy plane and be positive, and some of the volume will be below the xy plane and will be negative. Remember when we did the integral of sine of x from 0 to pi? That was fine. But when we did it from 0 to 2 pi, this area and that area canceled each other out, and we got a zero. Even though there was actually physically volume there, we got a zero. That's the same thing that happened here. I will say that if I try and do this problem in the other order, integral from 1 to 2, integral from 0 to pi, um, y sine of xy dy dx. Well, please notice the integrand here. The integrand here is a product. It's y times sine of something y. Oh, crud. If I have y times sine of y, that's integration by parts. And what's worse, it's double integration by parts. So if I want to do this way, this requires integration by parts twice. I absolutely don't want to do that. So sometimes our problems end up really nice. Sometimes our problems end up really sucky. We're going to have to spend some time figuring out which way to do this. Questions? Well, nobody's here to ask questions. So I'm screwed. I can't do this. I do note something. This problem was substantially less pleasant than this one. I want to look at this one again for a second. The integral over the rectangle R of x sine y dA, where the rectangle R went from 0 to 2 in x and 0 to pi over 2 in y. Now, we did this both ways. We did this dx dy, we did this dy dx. For the moment, I'm just going to go back and look at the one I did the first time, which was dy dx. If I rewrite this to be the integral dy dx, then the inside is dy, so the inside numbers are 0 and pi over 2. The outside is dx, so the outside numbers are 0 and 2. But that means I'm going to integrate with respect to y first. And x is a constant as far as y is concerned. And a couple of pages ago, I said we had these properties. And if you had a constant, you could take it out. This is a constant only in terms of y. So I can do this. See how I pulled the x out of the part that only needed y? Now this whole thing right here, that's a number. That's a definite integral. That's going to give me a number. And if it's a number, it's a constant as far as x is concerned. So I'm going to take this whole constant outside. bloody minute here. Instead of doing one integral inside the other, I was able to tease these two integrals apart completely. And here's where I say it again, Calc 3 is just Calc 1 with more letters. I'm doing a Calc 1 integral here. I'm doing a Calc 1 integral here. I'm not doing anything I haven't done before. But the only reason this worked is because up here, the integrand in this double integral is a thing in x times a thing in y. There is no mixing them together. This is a very nice corollary to Fubini's rule. If I can take my function of f of xy and rewrite it as a function of x times a function of y, then, oh, on some rectangle from AB cross CD, so here's my rectangle, just like it was before, then instead of doing the double integral over the rectangle of f of xy dA, I can do the integral in just x and multiply by the integral in just y. But it requires me to notice that my integrand is made up of multiplying two things together. And this corollary to Fubini's rule is on page 996 in the box labeled 11. The double integral of a product, one thing in x, one thing in y, is the integral in x times the integral in y. And that means I can just tease the two apart and not have to do them as one integral. Sometimes that's not easy to recognize. Double integral over r, xy squared over x squared plus 1 dA, where r is the rectangle 0 to 1 by -3 to 3. Oh, wait a second. This integrand is a product. This is x over x squared plus 1 times y squared. That's a g of x and an h of y. I can tear this sucker apart. This integral becomes the integral in x times the integral in y. Now I just have to put the appropriate limits on each part. And this is easy. This integral is a polynomial. This integral is a u substitution. So here I get 1/2 ln x squared plus 1 from 0 to 1. Here I get 1/3 y cubed from -3 to 3. Yay! So this is 1/2 ln of 2 minus 1/2 ln of 1. And over here I get 3 cubed is 27. 27 over 3 is 9 minus -9. ln of 1 is 0. So this is 18 times a half log 2. That's 9 ln of 2. Ta-da! But I have to be able to tell that I can tear the two pieces apart. And sometimes I can, and sometimes I can't. In this problem, the integral over r x, y, e to the x squared y dA, where r is the rectangle 0, 1 by 0, 2, I can't take that apart. If these were added, I might be able to rewrite this exponential as multiplying, but those are multiplied up there. I can't take the two terms, the x squared and the y, and somehow separate them from each other. So I'm going to have to do this either dy dx or dx dy. And my first reaction is, well, flip a coin, pick one. If I try this dy dx, then y on the inside is 0 to 2, x on the outside is 0 to 1. I look at this and I say, uh, e to the number y and then a y. This requires integration by parts. I don't like that. On the other hand, 0 to 2, 0 to 1, xy e to the x squared y dx dy. Well, then if I'm doing it dx first, this is number x squared. Wait, number x squared and then number x, that's a u substitution. U equals yx squared. Du is 2yx dx. Oh, I have a yx. I just need to get the 2. I can do this. Yay! Unfortunately, I know of no quick way to master which way you should do it, except to look at a lot of them and try lots of different ways. One last note before we go. There's another formula that I think is very useful that we did before. Back in chapter 6, I believe, chapter 6, section 5, we did the average value of a function. And we said that the average value was 1 over b minus a, the integral from a to b, f of x dx. You took the integral and you divided by how long the length of the section was. And really what this did is it gave you some number, and this area here balanced out this area here. Kind of like you imagine it melting, and this would be the level of the water. Well, the same thing happens for double integrals. For double integrals, when I do an average value, I have 1 over the area of my rectangle times the double integral over the rectangle. Remember our snow problem? Oh, before I do the snow problem again, here's the picture at the top, page 997. I have this function of two variables, but if I melt all that down, it comes to a single level. See how parts of this are underneath and parts of this are above. If I flatten it out, that would give me the same uniform height. Remember, we figured out the entire area of the state of Colorado. No wonder that looks weird. I knocked my camera. If I do the average snowfall in Colorado, I would take 1 over the area of the state and then add up all the snow. So I could tell you on average, parts of Colorado got a lot of snow, parts of Colorado got a little snow. Take the average value and you can tell me the average amount of snow in the state. That solution is right here. We do all this average, we do the Riemann sum, and then we divide by the area of Colorado. About 13 inches fell across the whole state. So I really stand by this statement. Calc 3 is Calc 1 with more letters. I'm doing integration by parts. I'm doing use substitutions. I'm doing integrals we know how to do. I just now have to do two of them instead of one of them. Okay, this is for Friday, March 7th. So on Monday, you've got spring break, which means the next Monday I'm going to see you is the 17th. That's the review, question, and answer for exam two. And then we're going to do more of this on Wednesday in the exam. You'll hand in that, and then the exam will be Thursday. I believe that's the way we worked that out. I will see you all after break. I hope you have a good time.